Hello, welcome back. We're going to start talking about nozzles and diffusers. Now, a nozzle, let's start with that one first. These are going to be devices that you can put on your system, and basically they're going to change your velocity and your pressure just by the shape of the device. The device of a nozzle is going to have a varying cross-sectional area, and the velocity of the gas or liquid is going to increase in the direction of flow. Now, the way we usually draw this, or the way I draw it, would be something like that. So at the inlet, you're going to have a larger area than you have here at the exit. So 1 here is the inlet, and then at the exit, which we'll call it point 2, we've got flow coming out like that. All right, so notice it's got a change in cross-sectional area. So as you go along the nozzle, the area gets smaller and smaller as you go. And here I have an example of one right here. This came in the box with my hairdryer. I don't ever use this thing, but it came in there. So if you look at it, you can see what it looks like. It attaches to the end of the hairdryer. All the air goes through it, but what it looks like on the other end is this. So notice it's got a changing area. It's forcing the flow out so that it has some changed properties. Now what we get with the velocity at the exit, you will find that the velocity of that exit is going to be greater than the inlet velocity. So it's going to speed it up. You're basically forcing that air or fluid through this smaller area. It's going to cause it to speed up. Now with the pressure at the exit is going to be less than the pressure at the inlet. All right, so we've changed pressure and velocity just by attaching a device like this that has a cross-sectional area that decreases in the direction of the flow. So this is a simple way to change your properties when you need to do that. Okay, so the important thing to remember would be these two things here. A diffuser kind of does the opposite thing. We're still going to have a device that has a cross-sectional area. It's going to vary as you go through the diffuser. Now in this one, the velocity is going to be reduced in the direction of flow. Okay, so if we were to draw a diffuser, this one's going to look like that. So essentially it's opposite. So this would be our inlet, 1. And then this would be our exit. Let's call that 2. So notice they're kind of opposite. Now our inlet is smaller than the exit. The area is going to change as we go through the diffuser. And now since we've got this bigger opening here at the exit, our velocity at the exit is going to be less than the velocity at the inlet. All right, because you're think about letting all those fluid particles, they have much more area, they're spreading out, so they're not going to be forced through there as quickly. Now with pressure, the pressure at the exit is now going to be higher than the pressure at the inlet. So again, we've changed two properties just by changing the shape that the flow goes through. Okay, so it's going through different areas, and that's causing the change in the properties. Now, again, I have an example from the hairdryer. This is a diffuser that came with my hairdryer. All right, so it's got these crazy things on the end. That's not really part of it, but you can see it takes the flow here from the hairdryer, forces the air through this diffuser, and then it sends the air out in this much larger area. So this cross-sectional area is a lot bigger than this one. So by spreading the air out, it's going to reduce the velocity and increase pressure. Okay, So that's kind of, application of our mass flow equations that we've been talking about. So now let's actually apply them to those equations. The only work that's going to be involved with these devices, with our nozzles and diffusers, is going to be flow work. Potential energy effects, we typically can neglect those because those would be caused by an elevation change, which we won't really have. So our equation that we will use typically for this is going to be 0 because we're going to assume steady state conditions. So if 0 equals QCV dot plus M dot times H1 minus H2 plus the kinetic term. So V1 squared minus V2 squared over 2. Like that. Alright, so notice that WCV dot term went away. That's because the only work we have is this flow work. When we developed this equation before, we talked about flow work. That's all taken into account right here. And usually this Q dot term is going to be 0 unless it's stated otherwise. Whoops, I'm missing words here. It's assumed to be 0 unless stated otherwise. Alright, so this is just our steady state equation that we had in the previous section. We just kind of simplified it down to match what we will have with nozzles and diffusers. Alright, so now we have that. So I will see y'all in the next video for an example.